Hello friends, welcome to all of you to Geo Exam Corner YouTube channel. Today's topic is interior structure of Earth. In this section we go through mechanical and chemical structures, discontinuities and seismic wave shadow zones. For easy understanding, the Earth can be compared with a fruit. If we cut a piece of fruit in half, we can see it is composed of very thin skin, a seed of significant size located in the center, and the most mass of the fruit being contained within the flesh. Okay, cutting the earth, we could see a very thin crust and a core at the center, and the main volume is contained within the mantle. So, this is the core, mantle, and the outer thin crust. So crust, mantle, core. So this is the general classification, but the structure of the earth can be defined in two ways, by mechanical properties or by chemical properties. So considering the mechanical properties, the earth is divided into five: the lithosphere, asthenosphere, mesosphere, outer core and inner core. By chemically, the crust is mantle, transition zone, lower mantle, outer core and inner core. So where do we get these informations from? These are direct as well as indirect sources. The first one, the direct sources includes the first one, rock from the mining area. The depth drilled hole 12 km deep in northern Kola Peninsula, Russia. Rocks there were 2.7 billion years and temperature is 180 degrees Celsius there. Second one, the volcanic eruptions gives evidence of the informations about the upper mantle. Then xenoliths, these are the foreign inclusions in igneous rocks which ranges in size from a sand to a boulder, provides informations about the lower crust and the upper mantle. Then ophiolites, these are rich in iron magnesium silicate minerals that once originated deep within the earth's interior, now layering on the surfaces. So the direct sources are rocks, volcanic eruptions, xenoliths and ophiolites. Then the indirect sources, by analyzing the rate of change of temperature and pressure from the surface towards the interior, there are some indirect sources. First one, meteors, as they belong to the same type of material Earth is made up of. Second one, gravity anomaly, which is change in the gravity value according to the mass of the material, give us informations about the materials in the Earth's interior. Then magnetic sources, then the most important one, seismic waves. The shadow zones of the body waves, both primary and secondary waves, gives us information about the state of material of the interior portion. As I already mentioned, Earth has a chemical and mechanical based layers. In chemical classification, there is crust, mantle and core. Here, continental crust is 0 to 75 km in thickness, but oceanic crust is 0 to 10 km in thickness. The upper mantle is about 10 to 400 km in thickness is the upper mantle, and the intermediate transition zone is 400 to 650 km, and the lower mantle is from 650 to 7 to 890 kilometers. So there is a layer known as the deep double prime layer, which is this D layer is just on the lower mantle, just above the outer core. So this is the D layer. So then comes the outer core, which extends from 2890 to 5150 kilometers. So the Earth's radius is 6378 kilometers. So the inner core extends from 5150 to 6378 kilometers. So all this chemical classification. Then the mechanical layers includes lithosphere, asthenosphere and mesosphere, outer core and inner core. So this lithosphere is about 100 km in thickness, composed of crust and upper mantle. Asthenosphere extends from 100 kilometers and the Mesosphere extends up to 2900 kilometers and cover 56% of Earth's total volume. The Mesosphere covers almost 56% of Earth's total volume. So Earth interior is broadly divided into three based on its chemical properties, which are crust, mantle and core. So in chemical classification, first one is crust. Crust is ranges from 5 to 70 kilometers in depth. Nearly 1% of Earth's volume and 0.5% of Earth's mass is made up of crust. It's the outermost layer and that can be sampled directly. It's a relatively cold layer composed of calcium, sodium and aluminum silicates. It's rocky and brittle. Many rocks now making up Earth's crust formed less than 100 million years ago. However, the oldest non-mineral grain, about 4.4 billion years old, indicating that Earth has had a solid crust for last 4.4 billion years. So this is a figure of Earth crust. Here you can see the continental crust and the oceans are underlined by oceanic crust. The Earth crust is divided into continental crust and oceanic crust. So continental crust extends from 0 to 10 kilometers, while the oceanic crust extends from 0 to 75 kilometers. The continental crust is thicker, less denser, and mainly formed of silicon and aluminum. That's why it's notated as Cr. And oceanic crust is thinner, denser, and main composition is silicon and magnesium. The continental crust is composed of granitic type rocks, which is felsic, of sodium and potassium aluminate silicate rocks. While the oceans underline the ocean basin, oceanic crust is made up of mafic iron magnesium, mainly composed of basalt. The continental crust rises higher on the mantle than the oceanic crust. The continental crust floats on the oceanic crust. It sits in isostatic equilibrium on the magma and is divided into plates that moves relatively to each other. Then the oceanic crust sinks into the mantle to form basins. When filled with water, these basins form planet's ocean. All continental crust is ultimately derived from mantle-derived melts, though fractional differentiation of basaltic melt and assimilation or remelting of pre-existing continental crust. These processes occur primarily at magmatic arcs associated with subduction. So continental crust is made mainly by the fractional differentiation of basaltic melt and remelting of pre-existing continental crust. While the oceanic crust is made up of volcanic activity at oceanic ridges. The mid-oceanic ridges generated new crust at the rate of 70 km cube per year. Next layer is mantle. Earth's mantle extends up to a depth of 2890 km, making it the thickest layer of Earth. Nearly 84% of Earth volume and 67% of Earth mass is occupied by mantle. I already mentioned that the crust is only 1% of Earth's volume. Here the mantle is 84% of Earth's volume. Then it's ultramafic in composition, which means Fe and Mg silicates rich. Mantle is primary source of basaltic igneous rock found on surface. The mantle is divided into upper, lower mantle and which is separated by a transition zone. The mantle is predominantly solid but behaves as very viscous fluid in geological time. The pressure at the bottom of mantle is 140 gigapascal. Although solid, the high temperatures within the mantle cause silicate materials to sufficiently ductile that it can flow on very long time scales. Convection of the mantle is expressed in the surface through the motion of plate tectonics. The source of the heat is derived from plate tectonics are the primordial heat and the radioactive heat released by as a result of radioactive decay. So here you can see the convection cycles, convective cells of mantle. So the classification is upper mantle, transition region and lower mantle. The upper mantle extends from 10 to 400 kilometers. So from the bottom of the crust to 400 kilometers. The transition region extends from 400 to 650 kilometers and the lower mantle extends from 650 to 2890 kilometers. So 10 to 400, 400 to 650, 650 to 2890 kilometers. In the upper mantle, temperature ranges from 500 to 900 degrees Celsius, while the lower mantle has 4000 degrees Celsius of temperature. Then the composition. The upper mantle is composed mainly of MgFe silicates like olivine and pyroxene and other crystallizers at high temperature. So it's mainly made up of olivine and pyroxene. Then the transition zone is a source of basaltic magma and complex aluminium bearing silicate minerals containing calcium, aluminium and garnet. When cold, this layer is dense due to the presence of garnet. These minerals melt easily to form basalts which rise through the upper layer of the magma. So it is mainly composed, it's the primary source of basaltic magma and it contains complex aluminium bearing silicate minerals. So the lower mantle is mineralogically consists of magnesium silicate perovskite and calcium silicate perovskite and magnesium-woosite. These are the major minerals present on the Earth's lower mantle. Additionally, the lower mantle is composed of oxides of silicon and magnesium. Then there is a D layer, the lowest part of the mantle. It's the lower part of the mantle. Next to the core mantle boundary is known as D double prime layer. This is known as D double prime layer. The D double prime layer extends from 2700 to 2890. So here is the portion of D layer. So it has a thickness of 200 to 300 kilometers. Although it is often identified as a part of lower mantle, seismic data suggests that the layer might differ chemically from the lower mantle. The D double prime name originates from a mathematician K. Bullen designation for the Earth's layer. In his system, the alphabetical notations are given from A to G and the crust he named as A and the inner core is named as G. In his later publication, the D layer is again divided into two, which is D prime layer and the lower layer is the D double prime. So this the name of D double prime is given by K. Mullen's designation. The innermost layer is the core. The core constitutes nearly 15% of Earth's volume. Earth crust has only covered 1% of Earth volume as the mantle covers 84% of Earth's volume. But the core has 15% of Earth volume is covered and the mass of 32.5% of Earth's mass. The diameter of core is extended from 2890 to 6378, 2890 to 6378 kilometers. The thickness is 3488 kilometer thickness. Core covers 3488 kilometer thickness. The core is nearly twice as dense as mantle. Is the densest. The density is really high and is composed of iron and minor amount of nickel and sulfur. So there is a theory called dynamo theory which suggests that the convection in the outer core combined with the Coriolis effect give rise to Earth's magnetic field. So the core is responsible for the Earth's magnetic field. The solid inner core is too hot and to hold a permanent magnetic field but probably act to stabilize the magnetic field generated by the liquid outer core. The average magnetic field strength of Earth core is estimated to be 25 Gauss, 50 times stronger than the magnetic field at the surface. So we have discussed about the structure of the earth on chemical basis like crust, mantle and core. Now we are moving to the physical layers. The physical or tectonic layer. The physical property is a function of prevailing variation in temperature and pressure. Denser material settle to the center of the earth, leaving the lighter ones at the top. Based on these properties, there are major layers which are lithosphere, asthenosphere, mesosphere, then outer core and inner core. So here there are three mechanical layers can be seen. The mechanical layers include lithosphere to a depth of 100 kilometer, and then asthenosphere at the depth of 100 to 200 kilometers, and the larger mesosphere to a depth of 2900 kilometers. Then comes outer core and inner core. First one, the lithosphere. Lithosphere is the uppermost mantle and the crust together constitute the rigid layer of rock called lithosphere. So it's a rocky layer. The lithos is the Greek word for stone. The crust is the upper part of the lithosphere and the upper mantle is the lower part of the lithosphere. So lithosphere is the combination of uppermost mantle and crust. Lithosphere is thinner under oceans and thicker under continents. The lithosphere is broken into moving plates that contain world's continent and ocean. Base of the lithosphere and top of the next layer, the sudden asthenosphere, is marked by sudden decrease in velocity of both P and S waves around 100 kilometers. The lithosphere is about 100 kilometers in thick. The next layer is asthenosphere. There we could observe a decrease in velocity of both P and S waves at 100 kilometers. The next layer is asthenosphere, which extends from 100 to 200 km. Relatively narrow, mobile zone exists below the lithosphere and within the mantle. Asthenis is the Greek word for the meaning weak or plastic. Nearer to the surface of Earth, temperature is relatively high, but the pressure is relatively reduced. Thus, the mantle is partially molten, and accordingly, the zone is composed of hot, semi-solid material that can soften and flow. So, asthenosphere is a mobile and plastic phase. The rigid lithosphere is thought to be float or move above on the slowly flowing asthenosphere. The asthenosphere is likely the source of much of the basaltic magmas. Next one is mesosphere. Mesosphere is the layer below asthenosphere and includes majority of mantle. The layer is more of physical significance than the tectonic. The boundary between mesosphere and asthenosphere is marked by abrupt increase in the velocity of seismic wave at the depth of 400 km, representing a temperature and pressure change. The change is marked by a polymorphic phase transition, a change in the crystal structure of the olivine on the most abundant mineral within the mantle. So there is lithosphere, asthenosphere and mesosphere. Then comes outer core and inner core. The outer core has a thickness of 2260 km and inner core has 1228 km thickness. The total core has 3488 km thickness. The outer core extends from 2890 to 5150 kilometers. Here the inner core extends from 5150 to 6378 kilometers. The Earth has a radius of 6378 kilometers. So the outer core is hot and composed of electrically conducting liquid made mainly of iron and nickel. It is suspected that about 10% of layer is composed of sulfur and oxygen. So it's a liquidous layer and it's mainly composed of liquid iron and nickel. So the inner core is made up of solid iron and nickel and is suspended in the molten outer core unattached to the mantle. The temperature of the outer core ranges from 4030 degrees Celsius in the outer region and 5730 degrees Celsius closest to the inner core. The temperature of the inner core is about 5400 degrees Celsius. So the temperature of the Earth's core, inner core, is 5400 degrees Celsius. Next, the conductive layer combined with the earth rotation to create a dynamo effect I already mentioned that maintain the system of electric current, thereby creating Earth's magnetic field. So the dynamo effect created by the outer core, liquidous outer core, is responsible for the magnetic field. The only reason why iron and other heavy metals can be solid at high temperature is because their melting temperature dramatically decreases at the pressure present there. So the pressure present there is 330 to 360 gigapascal. So temperature of the Earth's interior. The temperature gradient is about 15 degree to 30 degrees Celsius per kilometer within the upper 100 kilometers. It then drops off dramatically through the mantle, increases more quickly at the base of the mantle, and then increases slowly to the core. The temperature is around 1000 degrees Celsius at the base of crust and 3500 degrees Celsius at mantle and around 5000 degrees Celsius at the earth of the center. Next, we are moving to discontinuities. There are first order and second order discontinuities. First order includes Mohorovičić discontinuity and Gutenberg discontinuity. Rest of others are second order discontinuities. The first one is Conrad discontinuity between the upper and lower mantle. Second one, Mohorovičić discontinuity between the crust and the mantle. It's between the crust and the mantle. Then repetitive discontinuity is between the upper mantle and lower mantle. Gutenberg's discontinuity is between the lower mantle and outer core. So Lechmann discontinuity is between outer and inner core. It's between outer core and inner core. 5 discontinuities: Conrad, Mohorovičić, repetitive, Gutenberg, Lechmann. And the first order discontinuities are Mohorovičić discontinuity and Gutenberg discontinuity. The Conrad discontinuity, it is the correspondence to the subhorizontal boundary in the continental crust at which the seismic wave velocity increases in a discontinuity way. The subhorizontal boundary in the continental crust. The Conrad discontinuity, named after the seismologist Victor Conrad, is considered to be the border between upper continental crust and lower one. The boundary within the Earth continental crust that can be detected seismically at about 10 to 12 km depth. The boundary separates the crust into lower basic layer and upper granitic layer. So this discontinuity can be observed at a depth of 10 to 12 km, which separates the upper continental crust and lower one. Second one is Mohorovičić discontinuity, also known as Mohor discontinuity. It marks the lower limit of Earth's crust, a discontinuous layer separating crust and mantle. It's a first order discontinuity. It was discovered in 1909 by Andrija Mohorovičić, a Croatian seismologist. The Mohorovičić discontinuity is the transition from lower to higher density silicates. So it's the transition from crust to mantle. The transition layer being 0.1 to 0.5 km thick, 5 to 10 km below the ocean floor and 20 to 90 km beneath the continents. Hence the crust is thicker under land and than under the oceans. The The layer has a temperature of 500 to 600 degrees Celsius at the base of continental crust and 150 to 200 degrees Celsius at the base of suboceanic discontinuity. Average density of is about 4 gram per centimeter cube. So this Mohorovicic discontinuity is also the boundary between felsic mafic rocks crust, and there is a seismic velocity around 6 km per second in crust, and the denser ultramafic mantle with a velocity of 8 km per second. So it's a the seismic wave has a velocity has a transition from 6 km per second to 8 km per second while it moving from crust to mantle. So the cause of moho is thought to be the change in rock composition from rock containing plagioclase feldspar to above to rocks that containing no feldspar below. Next one, repeti discontinuity. This discontinuity is between upper mantle and lower mantle. It's within the mantle and it's a second order discontinuity. Next one, Gutenberg's discontinuity. German geophysicist Benno Gutenberg discovered the transition zone between lower mantle and outer core. So it is the transition between mantle and core at the boundary of 2890 km, 2890 kilometers, marked by abrupt change in seismic wave. Here, P waves decreases in velocity while S wave disappear completely. This is an important discontinuity where S wave disappear completely and P waves decreases its velocity. The S wave cannot transmitted through liquids. S wave is only passed through solid, hence it is believed that the unit above the discontinuity is solid, whereas the unit below the discontinuity is molten in nature. The last one is Lechmann discontinuity, the boundary between inner and outer core, which occur at a depth of 5100 km, is known as the Lechmann discontinuity. It's a transition zone between liquid outer core and the solid inner core. We have two seismic wave shadow zones. So S wave shadow zones and P wave shadow zone. First one, S wave shadow zone. So S wave do not travel through liquid. They only travel through solids, and this gets stopped at core mantle boundary because the outer core is liquid, and there is a S wave shadow on the opposite of the Earth's opposite seismic source. An angular distance from the seismic source to the shadow zone is 103 degree on the either side. So total angular distance of the shadow zone is 154. So this is the angular distance, is 154, and which covers an angular distance of 154, and the angular distance from the seismic source to the shadow zone is 103 degree. Then the P wave shadow zones. The P wave do not travel through the liquids, so they can make it through the liquid part of the core because of the refraction that takes place at core mantle boundary. Waves that travel through the core are bent and form away from the surface, and this create a P wave shadow zone on either side from 103 to 150 degree. So here the P wave shadow zone, of an angle from 103 to 150 degree. Thank you.